Hello, everyone. Welcome to section 3.6. This section is on rational functions. We've got a lot of ground to cover for these, so let's go ahead and just get right to it. So as a reminder, a rational function is a function of the form let's call it r of x. It's going to be of the form p of x over q of x, where those that p of x and those q of x are polynomials. So for example, if we had like 2x to the fourth minus like 1/3 x squared maybe plus maybe the square root of 5x minus 8, so that's a polynomial, right? And if we have that over like minus x to the third plus x squared plus x, which is also a polynomial, that right there is a rational function. Okay, so our main goal for rational functions here is going to be, we want to be able to eventually graph them. There's a lot of steps to get to there. So let's go ahead and look at a simple case first. So let's go ahead and consider what is arguably the most simple rational function. F of x is 1 over x. We've kind of seen this before. So we want to kind of explore this function a bit. So let's ask, what happens as x gets really big? So what happens at the end behavior, right? So if we were to plug in numbers for x, and let's see what their outputs would be. So if we plug in, for example, 1, f of x is going to be 1 over 1, and that's just going to be 1. Okay, not very exciting. If we plug in 10, it's going to be 1 over 10. If we plug in 100, it's going to be 1 over 100. If we plug in 1,000, it's going to be 1 over 1,000. So you can kind of see here that as we make x really, really big, f of x gets really, really small. It goes to 0. And then if we do x going to negative infinity, we kind of see something similar, right? So if we do -1, we get 1 over -1. That's just going to be -1. If we do -10, we'll get -1 over 10. -100, -1 over 100, -1,000, -1 over 1,000. And so if we kind of look maybe at a graph of these points, this graph will obviously not be really to scale. The points kind of do this. So for this first example we did, this is like the x equals 1, f of x equals 1 point. And then as we go along the x axis like this, as we go further and further, we get closer and closer to 0. And then for the other side, it's the same kind of idea, except negative. So we can kind of see that as we make x really, really big in either direction, it kind of goes like that. Okay. So remember how, so recall, can't plug in 0 to f of x. That's because 1 over 0 isn't defined, right? 0 isn't in the domain of this function. But what happens as x goes to 0? So what happens as x is really close to it? So we can go to 0 from the positive side, so starting on the positive x-axis and going towards 0, or we can do 0 starting from the negative side and going towards 0. And so the way we usually denote that is x going to 0 and then a little plus here means x goes to 0 from the right, also called the positive side, which would be like starting here and going towards 0 like that. And then the other way to denote is x goes to 0 and then raised to a little minus, and that's x goes to 0 from the left or negative side. Just a little notation for you. We will be using this notation just throughout the next couple chapters and such occasionally. So I just wanted to clarify what that means. But let's go ahead and look at what we were originally thinking of. So for x going to 0 from the positive side, let's say x starts at 1, f of x we already saw, it's 1 over 1, this should be 1. But then if x is like maybe a tenth, then this is going to end up being 1 over, actually, let me write it this way. The fractions will be nicer. So if x is 1/10, then f of x would be 1 over 1/10, which is 10. If x is 1/100th, then f of x is 1 over 100, which is 100. And then similarly for 1,000, sorry, f of x will be 1,000. Okay. And then if we do x approaching 0 from the negative side, let's see what happens. So x, let's say -1, that's going to be 1 over -1, that's -1, just like last time. And then a negative tenth is going to be 1 over -1/10, which will be -10. And similarly, 1/100th is -100, and -1/1000 is -1000. So as we can kind of see that, like, as x approaches 0 from the positive side, f of x goes to infinity, it gets really, really big. And as x approaches 0 from the negative side, f of x goes to -infinity. It gets really, really big in the other direction. Really, really negative, right? And so if we go back up to our graph, we can kind of see that, like, from the positive side, f of x gets really, really tall, all the way up there. And from the negative side, f of x gets really, really down low, like that. And so it kind of looks like this. And so what we've discovered here is interesting. So as x gets really, really big, f of x does something particular. And as x approaches a certain point, f of x does something very particular as well. And so there's a name for this. These are called asymptotes. The asymptote that runs vertically here, that kind of prevents it from going to 0, but you can kind of see it shoots up and shoots down along this kind of dashed line. That's called a vertical asymptote. That's right here. And then the x-axis here is we can kind of see, like, as we go along x, we make x really, really big or really, really negative. We see that f of x gets close and close to this line. So this is what's called a horizontal asymptote. It's that line right there. So let's go ahead and write down these definitions. Let's make this formal. Okay, so the line x equals a, so remember x equals a is a vertical line, is a vertical asymptote of our function f of x if f of x or here, let me write that in a new line. If our function f of x goes to either positive or negative infinity as x gets closer and closer to that point A. So we call that a vertical asymptote. Similarly, the line y equals b, remember y equals b would be a horizontal line, is a horizontal asymptote. If, or sorry, of f of x, if f of x approaches that value b as x goes to plus or minus infinity. So as we make x really big or really, really negative, f of x gets closer and closer to this number b. Okay, so those are asymptotes. It turns out they're actually not that hard to find as long as you pay attention to the rules. So finding horizontal and vertical asymptotes. So let's go ahead and let r of x be a rational function. And let's go ahead and write it out. So let's say r of x is of the form, so polynomial over polynomial. Let's say the leading coefficient of the first one is a sub n, x to the n, so the degree of the top is n, plus a sub n minus 1, x to the n minus 1, plus dot dot dot, plus a1x plus a naught, our constant term. And then the polynomial on the bottom, I'm going to write as b sub m, x to the m. So m is the degree of the polynomial on the bottom, plus b m minus 1, x to the m minus 1, plus all the way down b1 x plus b naught. So if we have some rational function that looks like this, the vertical asymptotes of our function r of x are the lines x equal to c, where c is a root of the denominator. So for example, if 2 were a root of this polynomial on the bottom, then x equals 2 would be a vertical asymptote. The horizontal asymptotes, or sorry, horizontal asymptote falls into cases, 3 of them to be precise. So if n is less than m, so if the degree of the polynomial on the top is smaller than the degree of the polynomial on the bottom, then your horizontal asymptote is at y equals 0. But if n is equal to m, so if the degree of the polynomial on the top is exactly the same as the degree of the polynomial on the bottom, then your horizontal asymptote is going to be at y equals a sub n over b sub m. So that's where a sub n is this number right here, and b sub m is this number right here. So the leading coefficients of those two polynomials. Okay, and lastly, if n is greater than m, then no horizontal asymptote. Okay, So that's it for vertical and horizontal asymptotes. Those are the rules. You want to find all the vertical asymptotes, you just have to factor the denominator, figure out where the roots are. You want to find a horizontal asymptote, all you got to do is kind of just check, hey, what are the degrees of the two polynomials? And if they're equal, what are their leading coefficients? So fairly straightforward. There's a slight twist though. So if n is greater than m, so in that last case where we have no horizontal asymptote, the degree of the polynomial on top is bigger than the degree of the polynomial on the bottom. If that is the case, you might have a slant asymptote. So let's talk about that. So slant asymptote is exactly what it sounds like. It's like a vertical or horizontal asymptote, like the function gets really close to it at some point, except it's not vertical or horizontal. It'll be like on a slant, hence the name slant asymptote. So if you take your rational function, r of x, and you use long division. So if you were to take your rational function and you were to actually go through and long divide it out, and if you get something like this, where when you do the long division, r of x becomes a, where a is some number times x plus b some other number plus some remainder r of x over the divisor q of x. So if you do your long division and your quotient is a linear term, see how this is a linear term. Don't care what the remainder or whatever that looks like. Then ax plus b is your slant asymptote. So a slant asymptote, just to kind of see what I'm talking about when I say that word. Let's say we have some rational function. It's got a vertical asymptote there, for example. And let's say when you do this long division, you find that this line right here is a slant asymptote. So this is ax plus b here. Then your rational function might look something like, it gets really close to that line, and then it goes up and gets really close to that one. Might look something like this. There we go. So yeah, that blue line, they're both blue, but this one right here, that one is your slant asymptote. Okay. So let's look at some examples to kind of solidify these ideas in our mind. So let's say we want to find the horizontal, let me try again. Let's say we want to find the horizontal and vertical asymptotes of this rational function. So let's do negative 2x squared minus 8x minus 9. And let's say that's going to be over x squared plus 4x plus 4. So for the vertical asymptotes, our rule said that in order to find these, all you had to do was take the denominator, x squared plus 4x plus 4, and factor it, find its roots. And this actually turns out to be a perfect squares. So this factors into x plus 2, x plus 2. So this thing has a root at x equals negative 2. So this is one of our vertical asymptotes. There's only one because we only have one root. It's repeated, but that's totally fine. Okay. For the horizontal asymptote, so the degree of the top, the degree of the numerator, we see that that is 2, and so is the degree of the denominator. It's also 2. So that means that our horizontal asymptote is going to be y equals leading coefficient over leading coefficient. So those leading coefficients we see, we've got -2 here, and then secretly here there's a 1. So that's going to be -2 over 1, which is just -2. So y equal to -2, that's our horizontal asymptote. Okay, fairly straightforward. Let's look at an example of a slant asymptote, just to cover our bases. So let's say we want to find the slant asymptote of x squared plus 2x, and let's say that's going to be over x minus 1. So to find the slant asymptote of this, we need to go ahead and do long division. So we're going to go ahead and take x squared plus 2x, and we're going to divide it by x minus 1. Don't forget to add the plus 0 to make sure that all our columns will line up. And I'm just going to go ahead and go through this division really quickly. So it looks like we want an x up here, and so then we get an x squared minus x here. Subtract that away, 0, and then we get 3x. Drop that down, and then I think we get a plus 3 here, and then we get a 3x minus 3. Subtract 0 plus 3. Okay, so that division tells us that we can take x squared plus 2x over x minus 1, and we can write it as x plus 3 plus the remainder, which was 3, over our divisor, x minus 1. And so from here, we can see this thing right here is our slant asymptote. So x plus 3, or rather, y equals x plus 3 is our slant asymptote. So in this case, and we will talk about graphing rational functions in just a second, but just so we can get a sense of what this slant asymptote looks like for this case. It turns out that if you went ahead and found the vertical asymptotes of this as well, there's a vertical one right about here. And the slant asymptote we found is this line right here, I believe. And if you go ahead and graph this function, it looks something like this, I think. Cool. So that red one is our slant asymptote. All right. So that was all fine and dandy. So we want to go ahead and look at how we can graph these rational functions in general, and I think we've got a good number of tools under our belt. But before we begin to do that, let's look at a special case. And this is a special case that you're always going to want to check for. This is common factors. Okay. So if you factor the top and bottom, and you factor that numerator and denominator, you might be able to cancel factors. And you should. Otherwise, your graph will be wrong. So for example, let's say we had x squared minus x minus 6x, or not 6x, sorry, just minus 6. And let's say that is over x minus 3. Now you can go ahead and find the asymptotes and stuff and all those things like you would normally, but you'll end up doing incorrect work, because if you go ahead and factor the top factors, or the numerator factors, is x minus 2, x minus 3 over x minus 3. So we can actually cancel out those x minus 3s. And all we're left with is x minus 2. So the graph of this is actually just a line. So if we go ahead and graph x minus 2, I think it's going to look something like this. Okay. You do have to be careful though, because remember, when you're dealing with rational functions, we can't divide by 0. So actually, you can't plug in three to this. And because we can't plug in 3 to the original thing, we technically can't plug in 3 to this line. And so when you go ahead and graph this line, what you actually have to do is you have to come in here at x equal to 3 and make a little hole. So this is actually much easier to graph because we canceled factors. Sure, we had to make sure that we don't plug in 3 and the domain's right, but this is still much easier than trying to find all the asymptotes and stuff, as we'll see in just a minute. This is a good test question, so I recommend you keep an eye on this, check for common factors. Okay, but let's move on and let's talk about graphing rational functions. So let's look at an example. So graph the following. Rational function. By finding its asymptotes and zeros. And let's do 2x squared plus 14x plus 24 over x to the third plus x squared minus 4x minus 4. Okay, so real quick note, a 0 of this rational function is going to be a 0 of the numerator that is not a 0 of the denominator. If you did find a 0 that was a 0 for both of them, that means actually you have a factor that you can cancel, so you should do that. But a 0 of the rational function is just where the numerator is 0 and the denominator is not 0. That'll make the whole thing 0. So that's what we'll look for. But first, let's go ahead and find the asymptotes, because that will give us a lot of good information to graph. So let's go ahead and factor top and bottom. So the top was, or the numerator rather, was 2x squared plus 14x plus 24. Turns out it looks like I can pull a factor of 2 out of every term there. So that's 2 times, and this becomes x squared plus 7x plus 12. And then I think if you go ahead and use the AC method, you'll find that this comes out to being x plus 4, x plus 3. And then for the denominator, we have x cubed plus x squared minus 4x minus 4. I'm going to go ahead and use factor by grouping. I'm going to group them like this, I think is the easiest way. For the first two terms, I can pull out an x squared, and this becomes x plus 1. And then I think for the other term, I can pull out a minus 4. So this becomes minus 4 x plus 1. And then I pull that x plus 1 out for both terms. I get x squared minus 4 times x plus 1. And now that quadratic that's left over, this one right here, that one is a difference of squares. So this becomes x minus 2, x plus 2, x plus 1. Okay, so we factor the top and bottom. So our rational function, 2x squared plus 14x plus 24 over x cubed plus x squared minus 4x minus 4. Once we factored, we see that this is going to be 2x plus 4, x plus 3 over x minus 2, x plus 2, x plus 1. Okay, so note there are no common factors. If there were common factors, we would cancel them out, and then we'd work with the simpler rational function left over, making sure we kept the whole in the domain. But since there aren't, we just proceed as normal. Okay, so the roots of the numerator there we go. Those were -4 and -3. And the roots to the denominator were ±2 and -1. And so what we have here is these, the -4 and -3, those are the roots of our rational function. And then these bad boys right here, these are our vertical asymptotes. Okay, cool. So let's actually go ahead and start making a graph for this since we've got some good information. And make it nice and big. Okay, so the roots of our polynomial are -4, -3. So let's go ahead and graph those. Those will be here and here. Okay. The nice thing about knowing where the roots of your rational function are is that now we know that it's not going to cross the x-axis anywhere else. So if we draw a graph and it crosses the x-axis somewhere else, that means we've done something wrong. Okay, and then our vertical asymptotes are at ±2 and -1. So those would be here and here and here. Okay, so we're making pretty good progress on this. Now let's look at the horizontal asymptotes, or the slant, depends. So let's see, the degree of the numerator, that one is 2. It's a quadratic on the bottom. And the degree of the denominator, I can't say that word right today for whatever reason. That was 3. And since 3 is bigger than 2, the degree of the denominator is bigger than the degree of the numerator. So if we look back at our rules, it turns out we have a horizontal asymptote at y equals 0. So we'll make that red on our drawing. So that's the x-axis right here. Okay, I just labeled it so we don't forget that there's something there, because it'd be kind of hard to see those colors against that white. Okay, so now we've got a whole bunch of information, but like, where do the lines go? Should I draw something here? Should it be here? Like, don't really know yet. So what I'm going to go ahead and do is use test points. And the test points that I'm going to use are, so you only need to figure out where the rational function is going to be in each sort of section. So I need to figure out where it's going to be here, 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 and here. So I need 1, 2, 3, 4 different test points. Okay, so for the first one over here, it looks like I can use the test point 1, 2, x equals 3. So if we look at that test point there, so if x equals 3, then if we plug in 3 to our rational function, I'm not going to run through the arithmetic because this is already a longer video. It turns out we pop out 21/5, which is 4 1/5. Okay, so we know that at x equals 3, our rational function is 4 1/5. So that point is right about 1, 2, 3, 4. It's going to be right about here. Okay, and so remember what I said about, we know where the roots are. It can't cross the x-axis. It can't cross the vertical asymptote. So we know that the graph of this function needs to look something like this. Okay, cool. That's one section done. Let's move on to the next one. So for this middle section here, it looks like I can use the easiest point, x equals 0. So if x is equal to 0, r of 0 is going to turn out to be -6 if you plug it in. So if we graph that point, 1, 2, 3, 4, 5, 6, that's going to be right about here. And I know that it's going to kind of look like this. When graphing rational functions, you don't have to be extra precise. As long as you have the basic idea down with the roots, the asymptotes, and the test points. Like in theory, this thing could be really wiggly and weird here. I don't really care about that. As long as you have the basic idea down, that's perfectly fine. That's really all we care about. Okay, for the next section, this thing right here, pretty narrow. It looks like a good test point to use would be like -1.5. So let's go ahead and do that. So if x is -1.5, we plug that into our rational function. Eventually, we pop out 60/7, which is about 8.6. So if we come back up here, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be right about here. It's pretty high up, but it's above the x-axis, so it's going to look something like that. Okay, and for our last section right here, let's go ahead and we don't want to use a root because that doesn't really tell us any information. I'm going to go ahead and just pick this point right here. That's x is equal to -2.5. So if we plug in x is equal to -2.5, our rational function spits out -4/9. Okay, so that's a negative number. And so if we go in here, that's going to be right about here. Okay. And now those roots have multiplicities. One, it turns out that it looks kind of like this. And that's going to approach the vertical asymptote. And if you're unsure about how this curves exactly, you could find another test point here, which would be good. Another test point here on the other side of the root. But just in the interest of time, that's what it looks like. And if you want more clarification on how to graph things around roots like that, I recommend you take a look at section 3.2. And there we go. We graphed our first rational function. It's a lot of work, but it's good skills. This can be really confusing. Let's go ahead and just finish this up by writing down what the basic steps are that I took to get there. Luckily, they're short to write down. So the first step is just factor top and bottom. And then make sure that after you factor, you cancel like terms. The second step after you've done that is from the factoring, find the asymptotes and the zeros using the skills that we've talked about in this section. And then number 3 is use test points and the above information to graph. Okay, 3 steps. Look straightforward, just takes a lot of time. Let me know if any of this didn't really make sense. I'm more than happy to chat with you about it, especially because this stuff is it's dense. There's a lot of moving parts going on here. Yeah, so good luck getting some practice in the homework, and I'll be in office hours if you need anything.